What's up, AP Physics, the Electricity and Magnetism student? Welcome back to our Elegant Physics videos. Today's topic 11.5 Compound Direct Current Circuit. So let's jump right in. Batteries with the same BMF. Now, batteries can be connected in different ways. Actually, we have two types of connection here, the series connection and the parallel connection. And the reason why we need to connect them in this way, actually, we have two reasons: to control the electromotive force and to adjust the electric current flowing through it. So the first type is the series connection. The batteries are connected in series when the positive terminal of each cell is connected to the negative terminal of the following cell. So here, the positive terminal of the first cell has one terminal in common with the negative one, and the positive terminal of the second cell is connected to the negative terminal of the second cell, and so on. The total voltage EMF of the system, which is consists here, for example, of three batteries, is the sum of the individual battery voltages. So we can write that the total VMF is equal VMF1 plus VMF, the second battery, and the VMF for the third battery, and so on. Now, what about the advantage and disadvantage here? The advantages are increased voltage to power devices that require higher EMF than a single battery can provide. Now, the disadvantage is if one battery fails, the entire circuit breaks and no current flow. Unequal batteries can cause overload or reverse charging, damaging weaker cells. And also, the current will be limited in capacity and only as much as a single battery can provide. Now, the second type of grouping is the parallel grouping. A set of batteries is said to be connected in parallel when the positive terminal or the positive terminals of all cells are connected together and their negative terminals are also connected together. So as you can see here, all the positive terminals are connected to one point, and on the other hand side, the negative terminals are connected to one singular point. The total voltage of the system remains the same, and the reason because all of these batteries are connected in parallel. Recall that to connect elements in parallel, we must connect or we must have two terminals in common between two elements. So here, for example, the first battery has two connection or two terminals in common with the second battery, and the second battery has two terminals in common with the third battery. So they are considered to be connected in parallel, and the potential difference across the first battery, second, and the third battery is the same. So VMF is equal the VMF1 equals VMF2 equals the potential difference across the third battery, which means equals to the VMF3. Now, what about the total current? The total current capacity increases. The combined current is the sum of the individual battery currents. So I, the total, is equal I1 plus I2 plus I3. So the first battery will send current I1, the second I2, and the third I3. The summation of all of these currents will make up the current I. Now, the advantages and disadvantages. The advantages are it may extend the battery life, increase current capacity, and maintain the same voltage but supply more current safely. The disadvantages, if batteries have different voltages, so in both cases, whether you want to connect them in parallel or in series, make sure that you have the same electromotive force or the same potential difference, because current may flow between batteries here in this case, causing overheating or damage. Another disadvantage does not increase voltage, so it's not suitable when higher voltage is required. So we tend to use the series grouping instead of this. Now, section 2, ideal versus non-ideal batteries. Now, an ideal battery have negligible internal resistance. The terminal voltage or the electric potential difference across an ideal battery is the same whether the battery is connected in a closed circuit or an open circuit. So here in this case, for example, we have cell or a battery, and this battery does not form any closed loop with another electric circuit or with another electrical element. And here we have connected a voltmeter across this battery to see how much will be the potential difference. Now, here we have connected the battery with two lamps, for example, in parallel. You can connect the battery in series or in parallel, it doesn't matter. But what is matter here is the thing is we have the battery now with in closed circuit. So we have now closed loop, which means the current will flow. However, if we connect the voltmeter across the battery here, we will find that the reading of the voltmeter in this case, when the circuit is closed, is the same as the reading in the voltmeter when the circuit is open. Now, what do we call this reading? This reading represent what do we call it as the terminal voltage or the electromotive force, or you can call it the electric potential difference across the ideal battery. Now, another common name for the terminal voltage in this case for the ideal battery is the electromotive force, and it's denoted usually by E. So in summary, always and forever for ideal battery, the delta V of the battery, whether the circuit is closed or opened, it's equal to the delta V of the terminals, and it's equal to the electromotive force. So different names for the same quantity, and regardless whether the circuit is open or closed. Now, for the real battery or the non-ideal battery, it can be modeled as an ideal EMF in series with a resistor. This resistor represents the internal resistance of the battery. So now, for the real battery, we have internal resistance here. Usually in AP exams, we use this boundary to represent the internal structure of the battery. So here the battery consists of the internal resistance and the E or the battery symbol itself. Now, in case we have open circuit, then we can deduce that there's no any current flow because we don't have any closed loop. And the voltmeter will measure for us directly the electromotive force. So when we have open circuit, the measured voltage will be electromotive force, or in other words, the delta V of the terminal, the potential difference, or the voltage of the terminals will be equal to E. Now, what will happen if we connect this real battery or non-ideal battery to a closed circuit? Now, if we uh, compare the reading in the voltmeter, in this case with the reading in the case where we had open circuit, then we're going to find a difference. And the current, because the current will lose some potential equal to IR, so some of this potential provided by the E, by the electromotive force, by the battery, will be lost or will be dropped because of the internal resistance. And to calculate how much potential will be lost, we can use Ohm's law because this resistance usually obeys Ohm's law and it's equal IR. Now, to find the potential voltage in the case where the circuit is closed, we just simply find the difference between the electromotive force provided by the battery minus the amount of potential that the resistor will uh, drop or will consume. So delta V of the battery is equal to delta V of the terminal now, and this formula is applicable only if the circuit is closed for a real battery. Now, for a closed circuit, in case of we have real battery, the delta V terminal will be equal to E. Remember that the main current at any instant, and regardless of the type of the battery, it can be written as the electromotive force over the R equivalent. Now pay attention here, the R equivalent will consider all the resistance included in the battery, and these resistors involve the internal resistance of the real battery if it's existed. Now, the relationship between the terminal voltage of the battery and the current in the circuit can be obtained from the equation delta V terminal is equal E minus Ri. Now, from this equation, one can say that as the I increases, the whole term here will increase, which means the E minus Ri will be less because this term will increase, which means we're gonna drop more potential difference from the electromotive force. So as a result, the delta V terminal will decrease. And this is exactly equivalent to a linear equation where the delta V terminal is y, the epsilon is b, the r is the slope, and the I is the x. So y represent the vertical axis here, and this is equal to the delta V terminal. The b is the vertical intercept, and usually the vertical intercept will represent the electromotive force. Now m is just the slope, and here in this case the slope will be equal to minus r, so we should expect to have negative slope. And the x is the horizontal axis, and this represents the current. Now, as the current increases, the terminal voltage decreases linearly because of the voltage drop IR across the terminal resistance, as I explained earlier. Now, the graph is therefore a straight line with a negative slope, and here is an example for this graph. So we have a plot the potential difference or the terminal voltage across the vertical axis and the current across the horizontal axis. As we can see here, the slope of this graph is negative, and the slope here represents the minus r. Now, the interpretation, the decrease in the terminal voltage occurs because part of the battery's EMF is used to overcome the internal resistance inside the battery, leaving a smaller potential difference available for the external circuit. So here, in this case, when we have a situation where the real battery is involved, so this battery will provide E, and this internal resistance will drop this E by an amount IR, according to Ohm's law. If we find the difference, then the output voltage will be less than the provided one by the battery because of the internal resistance. So only smaller part of the potential difference will be available to feed all the electric circuits. Now exercises. Exercise 1. When battery is connected to an external resistance capital R as shown above on the left. So here in this case, we have real battery connected with resistor in series, and the current here will be in the circuit will be I. When the external resistance is changed to 3R, so in the second trial, we have changed the resistance, so we have increased the resistance to 3R. According to Ohm's law, we should expect to have less current now, and the current will be I over 2. What is the internal resistance of the battery? So they want us to find the internal resistance of the battery, and as we can see here, all the choices are written in terms of R, capital R. Now let me remind you that this battery will provide the delta V terminal, which is equal to E minus Ri. And for this battery, the delta V terminal will be equal E minus R times the current, and the current here is I over 2. Now remember that the delta V here of the terminal will be feeding the resistance R, because as we can see here, this battery is connected in parallel with this resistance, so we should expect that the delta V terminal will be equal to the delta V of R. However, the delta V of R, if you want to find it, we just write Ri, which is exactly equal to the delta V terminal. So we can write now instead of delta V terminal, IR. So let me write here, this is just the Ri or IR. And using the same argument, one can say that the delta V terminal can also be calculated using the delta V of this R, the 3R, which is equal the 3R times the current, which is I over 2. So I have applied only Ohm's law here. We know that to apply Ohm's law, we need to consider the resistance times the corresponding current. The resistance here is 3R and the corresponding current is I over 2, which means 3 over 2 Ri is the potential difference across the delta V terminal. So let's replace it here. Now we can just move in these two equations. We just need to move this to here and this term back to here. So from the first equation, this is the second equation. From the first equation, we once can deduce that the Ri is equal, or sorry, it's a plus Ri, which is equal to E. So after we have removed minus Ri, it becomes a plus. And from the second equation, 3 over 2 Ri. Now Ri over 2 can be written as half of Ri. Now if we move the minus half of Ri to the other hand side, it becomes a plus half of Ri, which is equal to E. Now we can equate 1 and 2 together because E and E there is the same. Now, because we have used the same battery in the second trial. So we know that the E is equal to E. Now from the first equation, we have Ri plus Ri equals, from the second equation, we have 3 over 2 Ri plus half Ri. Now from this equation, we can take I as a common factor. So now we can cancel simply I with I. Now we move the like terms, so R, we move it to this side, and half of R, we move it in that side. So R minus half of R equals 3 over 2R minus R. Now we can take R as a common factor. So here we're left with 1 minus half equals R as a common factor, 3 over 2 minus 1. Now 1 minus half is half multiplied here, R multiplied by 3 over 2 minus 1, it's half. Now half with half cancelled out, and the final answer will be R equal R. So the correct answer will be C. Now question 2, the circuit represented in the figure above contains 4 resistors and a battery. The 45-volt battery has 1 ohm internal resistance. How much energy is dissipated by the battery's internal resistance? We know that the energy is denoted by E. It's given by P times T. Now P for the internal resistance, according to Ohm's law, it's given by R times I squared. But since here we are dealing with a small r, so we just need to change the letter from capital R to small r. And substitute it in the equation. The formula becomes R times I squared times T. So this is how we calculate the electrical energy dissipated by the internal resistance. We have the time, we have how much internal resistance in the battery, but we still need to find the current. And here the current is represent the main current, because the main current is the current that will be delivered to the to the internal resistance. Now, to find the main current, we always follow this strategy. We just apply the electromotive force over the R equivalent. Now, R equivalent represent the equivalent resistance for all resistor or resistance in the electrical system. And when I say all electrical resistance or all resistance, I mean by that including the internal one. So how many resistors here we have in the system? We have 1, 2, 3, 4, and the internal resistance. Then we have five resistors. Now we have R1, R4, and the small r are connected in series because we have one terminal in common between them, and they are drawing the same electric current. So the main current will transverse here, the same current as well as here and as well as there. So let's find out what will be the total for these three resistors. The total will be 8 plus 2 plus 1, and the answer would be 11 ohm. Now 11 ohm is not the R equivalent, we still need to add this system. Now 6 and 12 are connected in parallel, and to find the R equivalent for this part, we just find the product over the summation of these resistors, and the answer is 4 ohm. So we will end up with this equivalent resistors. The first resistor is 11 ohm, which, which is consists of the combination between R1, R4, and small r, and the 4 ohm after we have combined R2 and R3 together. Now, these two resistors are connected in series, and the R equivalent then will be 11 plus 4. The electromotive force here is 45, so it becomes 45 over 15 is the equivalent resistance, and this means the current will be 3 amps. Now, let's substitute in the equation again. The internal resistance is 1, the current is 3 to the power 2, and the time is 60 seconds. The final answer will be 540 joule. A resistor of resistance R is connected in circuit to two identical batteries. The circuit also contains a switch S and ideal voltmeter V. As shown in the figure above, the batteries both have the EMF E and internal resistance, so same electromotive force and same internal resistance. The reading of the voltmeter is noted with the switch is in the open position. So in the first case, the switch was open and the voltmeter is connected directly with the first battery. Remember that this battery is real battery. And in the case where we have open circuit, the circuit here is opened and the battery is not forming any closed loop with another electrical component. And we know that for the real battery, in the case of open circuit, the delta V terminal will be purely equal to electromotive force. Now, which of the following best represent how the voltmeter reading after the switch is closed? So after we close the switch, the two batteries becomes in parallel, and the two batteries will have the same electromotive or the terminal voltage. So the terminal voltage here is equal to the terminal voltage there. However, in case we have a closed loop, the terminal voltage is no longer equal to E. It will be E minus IR. And we know that E minus RI or IR is less than E. And we can say that the reading of the voltmeter is lower. Now, two resistors of resistance R and 12 ohm are connected to a battery. As we can notice here, R and the 12 ohm are connected in parallel, and both of them are connected in parallel with the battery. This battery is an ideal battery because it consists of the electromotive force with an internal resistance. The battery of EMF 18 volt as shown in the figure above. The battery has internal resistance R, so this represents the E. The current in the battery is 1.5. This is the main current actually. And the current in the 12 ohm is 1 amps. Let's call it 1 across the 12 ohm. We need to know what is the internal resistance of the battery. To find the internal resistance of the battery, let me remind you that the delta V terminal of the battery is equal E minus Ri or I times R. Now we need to find R. We have the main current, the current that is traveling through R, it's 1.5 amps. The electromotive force is also given, but we don't know what is the delta V terminal. Now the delta V terminal here is the same as the delta V across the resistor R, which is equal to the delta V across the 12 ohm. So remember that since they are all connected in parallel, the delta V terminal will be the same as delta V of R, which is equal to the delta V of 12 ohm. So the easiest way to find the delta V terminal is by finding the delta V across the 12 ohm. So the delta V terminal, it's equal to delta V of 12 ohm, and the delta V of 12 ohm according to Ohm's law is the resistor or the resistance of the 12 ohm multiplied by the current across the 12 ohm. The resistor of this 12 ohm or the resistance is 12. The current is 1. So the voltage is 12 volts, which is exactly the voltage across the 12 ohm, the resistor R, and the battery. So now we have the 12 to be the delta V of the terminal. Let's substitute back here. 12 is equal, the electromotive is given by 18. minus the resistance is unknown and the current is 1.5. So we move 18 to the other hand side. 12 minus 18 is equal minus R 1.5. We move the minus and 1.5 to the other hand side, so we divide over minus 1.5. Minus with minus cancelled out, 1.5 and 1.5 cancelled out, and the R actually equals to 4 ohm. A battery with non-negligible internal resistance, a variable resistor, a voltmeter, and an ammeter are connected as shown above. So the voltmeter is connected across the terminal of the battery to measure the V terminal. The ammeter will measure for us the current in the circuit, which means the current through R and the current through the internal resistance R. What is the internal resistance of the battery? The graph above on the right shows the voltmeter reading as a function of the ammeter, so it will give us the variation of the V terminal across the batteries with the current of a variable resistor is changed. So how we can control the flowing of the current? Can be done by changing the R. This is how we control the flowing of the current. Now we need to know what is the internal resistance of the battery. Now, since the graph represent information about the V terminal and the current, which is exactly the same current flowing through the small r, then the slope will represent the minus r. So let's find the slope. The slope equals, we need to take 2 points. The 2 points are 0, 12, and 8, 8. Make sure that the units are consistent. So here we have SI unit and the vertical axis SI unit. So for sure the final answer will be expressed in SI unit. So 8 minus 12, 8 minus 0, and minus r, which is the slope, is equal minus 0.5. Now minus with minus cancelled out and the r is equal 0.5. What will be the unit? Since everything is expressed in SI unit, the answer will be SI unit. And the SI unit for the resistance is ohm. So the correct answer is 0.5 ohm. Student has an ohmic light bulb, so this light bulb obeys Ohm's law. Connected to a battery that has significant internal resistance. So it has internal resistance, so this is non-ideal battery or real battery. As the student connect other identical light bulb in parallel to the first light bulb, which of the following could be a reasonable observation about brightness of the light bulbs? Now, by connecting more light bulbs, it means the total internal resistance will be less. We know that setting the light bulbs or resistors in parallel, it will reduce the R equivalent, which means it will increase the current. Now, by increasing the current, the delta V terminal, which is equal I minus Ri, increasing the current, it means this term, which is negative, it will be much more. And the difference will be less. So more potential will be dropped from the electromotive force of the battery, which means we'll be able to deliver less potential across each light bulb since they are connected in parallel. And we know that there is a proportionality between the potential difference and the lightness of the lamp. And we can say that each light bulb gets dimmer as more light bulbs are added. Adding more light bulbs will reduce the R equivalent. Reducing the R equivalent will increase the main current, and increasing the main current will reduce the delta V terminal. So the correct answer would be B. Now, both two batteries have the same EMF, but one battery is an ideal or is ideal, while the other battery is non-ideal. The batteries are connected to identical resistors. Does the resistor connected to the non-ideal battery have the same or less current compared to the resistor connected to the ideal battery? Do you think the current here in the first battery will be equal or less than the current here in the second battery? What evidence or reasoning helps support the claim? We know that the current according to Ohm's law, we are talking here about the main current. The main current can be calculated via E over the R equivalent. So more R equivalent means less current. And when I say R equivalent, I mean by that the combination, it consists of all the electrical resistance from every single resistor included in the electric circuit. Now here we have two resistors if we compare it with the first case. So we have more R equivalent, more total resistance, so which means the current will be less. And the correct answer will be, we will have less current, so not B, not A. And some of the current in the non-ideal battery goes through the internal resistance. This is not true because it violates the conservation of electric charge. Current cannot be consumed in the internal resistance. So D will be correct. And let me read the statement of D. Less current because the non-ideal battery's internal resistance adds to the external resistance. So these two resistors will be added to make a higher equivalent resistance for the circuit, which means the main current will be less. And that's it for today's lesson on 11.5 compound direct current circuits. Thank you for joining me. See you next time.